What's up, guys? Welcome back to another paper walkthrough, and in this one we're taking a look at ProGAN, which is one of those sort of revolutionary papers in GANs. And yeah, as always, I should say, we're also going to implement this one in the next video. So yeah, if you really want to understand ProGAN in depth, then watch this video, because we're going to go through the details of it, and then in the next video we're going to implement it all from scratch. So, without further ado, let's get started. Paper title of this one is Progressive Growing of GANs for Improved Quality, Stability, and Variation. And it was released, I think, in the end of 2017, but don't quote me on that. I might be wrong there. But so in the abstract, they mentioned that in this paper, we're going to describe a new training methodology for GANs. And so the key idea is to grow both the generator and discriminator progressively, where we start from a low resolution and we add new layers to that model increasingly fine details as training progresses. So this is one of those ideas that really kind of makes sense. So specifically, what they do is that they start with learning to generate a very small input image. So an image of 4x4. So we ask the generator to generate 4x4 images, and then when it has sort of achieved that task where the target images look very close to the generated images at this specific resolution, then we sort of upgrade it and we ask it to generate 8x8 images. And then when it's finished with that challenge, we sort of upgrade it again to 16x16. And you can imagine this continuing until we eventually reach 1024 squared images. So really, really high quality images. And I guess I don't know, there's something about this idea that just really makes sense, because it's similar to the way that we learn, right? I mean, if we take mathematics, for example, you don't sort of at day one ask them to be able to calculate gradients and stuff. You couldn't start at the very basics of counting and sort of addition and 1 + 1 and so on, and then you sort of with building blocks you advance and ask it to do progressively more difficult things. So that is the key idea, but additionally they also describe several implementation details that are important. So it's not just this idea; they actually have multiple ideas. So let me draw them or sort of write them up. So one is definitely this progressive growing. So that's sort of the key idea, right? So we should maybe do a star on this one. That's sort of the main idea. But then they have other ones, which is I guess this is not in order of importance or anything, but they do introduce this MiniBatch Std. So basically, this is something that we send into the discriminator, which captures sort of the variation of the generated images. So the idea is that this will force the generator to be able to generate more varied images than just sort of the same images all over again. So that's one of the ones. And then let's see if I remember. So we have PixelNorm. So that's sort of a new normalization method that is sort of instead of using something like batch norm, which is commonly used. And then the fourth one is equalized learning rate. And so we're going to go through the paper and we're going to see what all of those are. But those four are the main components of this paper. So, as always, I want to make these videos as compact as possible so that we understand how it works and sort of the material that's needed for us to understand the implementation and to actually implement it. So that's also why I'm going to skip major parts of this paper, but it is going to be in the description if you want to check out by yourself, so to speak. So I'm just going to move on. And I'm just going to focus on this sentence here. Our contributions are largely orthogonal to this ongoing discussion. So, up to this point, it's sort of been mostly about the loss, sort of VGAN, VGAN GP, LSUN loss, and sort of those things. But they noticed that it doesn't really matter which loss they use. So this methodology is orthogonal. It's not really related to the loss function too much, but they do use vgan GP. So then, yeah, the progressive growing is the main part. So the primary contribution is that we start with the low resolution and then progressively increase the resolution. And also the generator and discriminator networks are mirror images of each other. So, you can sort of view it that the generator is going to increasingly expand, right? It's going to be 4x4, then 8x8, then 16x16. And similarly, the discriminator is going to take in 16x16, then reduce it to 8x8, and then 4x4. So we'll see exactly how it looks like later on. But in many ways, the generator and discriminator are sort of the opposites of each other, sort of mirror images. And yeah, I think this image right here, this figure, describes it quite well. So the training starts with 4x4. So we start, over here. And then we basically generate 4x4, and then we send in 4x4 here to the discriminator. So then after sort of progressing to the next level, we run it through the 4x4 layer, and then we add this additional sort of new layer with it, which is this 8x8 sort of conv layer. And then the generator, the discriminator takes in this 8x8 and then reduces it to 4x4. And we sort of continue doing that, right, for several steps until we eventually reach this 1024 squared image. And yeah, I guess here, here it's kind of clear that they are mirror of each other's. And then here you can see some examples. So, this looks good. And yeah, I guess also, yeah, so one thing they also mention here is that all existing layers remain trainable throughout the process. So you could imagine that, after you train it to 4x4, you freeze those weights, and then you add another layer that you sort of fine tune. But when you add a layer, you train it end to end. So you train all of the layers. So a benefit of doing this as well that they observe is reduced training time. So this trains 2 to 6 times faster than if they would just sort of, I guess, ask it to do a resolution to start with. So then we move on to another thing, which is the increasing variation unit using MiniBatch standard deviations. So, we all know this probably, that GANs have a tendency to just sort of not show as varied images as in the training data. So their approach has neither learnable parameters nor new hyperparameters. So it's quite a simple approach. They first compute the standard deviation for each feature in each spatial location over the MiniBatch. So let's unpack this just a little bit. So what they do is that they calculate the standard deviation for every example across all of the channels and all of the pixel values. And then they take the mean value of that, and then they replicate the value. So they replicate the value and concatenate it to all spatial locations over the MiniBatch, yielding one additional constant feature map. So, all that they get here is a single value representing this sort of this standard deviation across all of the channels, all the pixel values, and then they take a mean across over the batch, and then they replicate that value, right? That just a single scalar value. They replicate that across all of the examples, and then all of the pixel values, and then this is a single channel, and then they just concatenate this single channel to our input. So it's quite simple, but it works pretty well, it seems. All right, so if we continue, we get to this sort of another idea. So we've understood that we do this progressive growing where we start by 4x4, 8, 16, etc. But there's also an additional thing that they do, which is, so the additional thing that we do is that when we add a new layer for a new resolution, we don't just sort of do that directly. We fade in that new layer by doing some sort of nearest neighbor upsampling, and then we do this with this new conv layer, and then we sort of gently add in this new conv layer. So yeah, so they mention here, I'm going to go to the figure, but let's just go to text for now. So when doubling the resolution of the generator, we fade in the new layers smoothly. So looking at this middle part, you can see here that let's say we have some 16 by 16 input, and then they do some upsampling. All right, so the upsampling is just nearest neighbor upsampling. And then we take two paths that we can sort of follow. The one to the left is just taking this upsampled image, right? Just sending it through this nearest neighbor. And then we run it through a conv that converts the channels to RGB, so to 3 output channels. The other path that it can take is go through this new conv layer, which is responsible for this 32 by 32 resolution, and then we send it to this RGB. So what we do then is that we do an interpolation of these two. So let me make this clear. So we have up, let's just say that's the upsampled image, right? And let's say that runs through an RGB, so it's RGB channels. And then we have this, let's call it out. So that's what's sort of out from this, right? So what we do is that the result of sort of this right here is that we take 1 minus alpha, and alpha is just some scalar value. We multiply that with up, and then we add alpha times out. All right, so we do an interpolation between the upsampled image and then out. So alpha starts at 0, and then we grow it to be alpha equals 1. So in the beginning, it's nearly only from this upsampled image, and with time we increase alpha so that the new conv layer is sort of smoothly transitioned in and takes more and more responsibility to actually, generate this new image. And then we do this similar thing for the discriminator, where we also downsample and do the similar thing, right? So we fade in this new layer for the discriminator, similarly, except that for upsampling, we downsample with an average pooling. All right, so that's what happens when we introduce a new resolution. But let's say we are sort of done fading in that one, then it will look like it does over here. So then we are just going to upsample, run it through this new conv layer, this 32 by 32, and then just send it to RGB, right? So this is only during training, and then we'll sort of get rid of that additional step, right? One thing that could be tricky here is that this RGB and this RGB are not necessarily the same. So we send it through right there. I'm doing a lot of arrows here, but this one is a conv layer that perhaps might change the number of channels. So if it changes the number of channels, then we we can't use the same conv layer, right? Because it's going to take two different in channels as input. So these two are not necessarily the same, and we'll see in the implementation. We'll see a nice way to solve that, or how we solve it. But that's just one thing to keep in mind. Yeah, and then we can see sort of 2 RGB represents a layer that projects 2 RGB colors, and from RGB does the reverse, and both use 1x1 convolutions. All right, so then we get to this normalization things, which is the third and the fourth thing I mentioned, which is PixelNorm and this equalized learning rate. So they mentioned that GANs are prone to escalation of signal magnitudes, and most, if not all, earlier solutions discourage this by using a variant of batch norm in the generator and in the discriminator, right? This is common. We've seen this multiple times. These normalization were originally introduced to eliminate covariate shift. So covariate shift, from my understanding, is when sort of the training data and the test data does not come from the exact same distribution. So batch norm helps with that by normalizing sort of as input to each conv layer. We're sort of guaranteeing that so we're in a way guaranteeing that the distribution is similar as input to each conv layer. But what they mention here is that however, we have not observed that to be an issue in GANs. And we use a different approach that consists of 2 ingredients, neither of which include learnable parameters. So the first they mention here is this equalized learning rate. And I have to be honest with you and say that, so how this works is quite simple, and we can implement it without too much trouble. And the intuition of why this works is somewhat clear, but exactly how this works, I'm not entirely sure of. So I tried coming up with some examples of the issues that they talk about here, but yeah, this one is one that I cannot say that I completely understand. But so let's try to understand this just a little bit. So what they mention is that they deviate from the careful weight initialization trend and use a trivial and normally distributed mean zero standard deviation 1 initialization, and then they scale the weights at runtime instead. So they scale the weight by dividing by C, where C is the prelay normalization constant from the HE initializer. So all right, so basically all they do is that they at runtime, sort of at the forward step of our sort of conv layer, is that we take our conv layer and we multiply everything with a scale, and the scale comes from the HE initialization scale that we get. So we do that every time at runtime. And the reason they mention here is that sort of there's a problem with optimizers, which is that Adam and RMS prop, they normalize. So the gradient update step of Adam and RMS prop is dependent upon the dynamic range of the parameter. So what that means is that it sort of normalizes based on the estimated standard deviation, but it doesn't take into consideration of the scale, sort of the magnitude of that weight. And basically they want to solve that, so they introduce this equalized learning rate, which is to do this forward in this forward step. We multiply with the scale from the initialization, and in that way we basically ensure that every weight is in the same dynamic range, and then the learning speed is the same for all weight. The intuition is somewhat clear. Exactly why is not clear to me, and I think that the issue that I also run into with this is that why didn't they perhaps try to modify the optimizer instead of adding this new sort of modified conv layer? And also I haven't, so this seems like a problem that is more related to you know, in general when it comes to Adam and RMS prop, and then this should be something that we should see in many different tasks, not only for GANs, I guess, but I haven't seen this anywhere else. And granted, I've missed a lot of papers, but you know, I haven't seen this except for this paper. And exactly how we implement this is pretty simple, and we'll see exactly how we do that in the implementation video. Then we move on to the second, which is pixel-wise feature and vector normalization in general in generator. So this is just PixelNorm, and the idea is to disallow the scenario where the magnitudes in the generator and discriminator spiral out of control. And they normalize the feature vector in each pixel to unit length in the generator after each convolutional layer. So yeah, I mean they use this formula, which is basically that they take the mean, so inside here, they take the mean of the pixel values for every channel. So the n here, let's see, yeah, the n right there is the number of feature maps, so the number of channels. So they sum over all the channels, and then they sum over all of the pixel values at a specific location. They take that, they sum over all the pixel values squared, and then they just divide by the number of channels, and then they take the square root, and basically they take the new pixel value at that location is the old one divided by this square root of the mean of all of the pixel values squared for that particular location. The implementation of this, again, is going to be pretty clear, and I guess this is a way to, I guess they were inspired by AlexNet paper, and they wanted to not use batch norm because batch norm has inherent problems. And so to get rid of batch norm, they use this instead. I mean, there are probably thousands of other ways to normalize, right? And they also mention here that they find it surprising that this heavy-handed constraint does not seem to harm the generator, and it doesn't seem to change the result much, but it prevents the escalation of signal magnitudes very effectively when needed. So I guess you can remove this and it still works most of the time. Then we're gonna move down, and this stuff is not too important, I think. And here we can see some examples. Oh, I even added a note here. This looks good, and you know, this does look good. It's 1024 by 1024 images, and they are, you know, a lot better than the previous results. So this was, you know, one of those papers that I think was pretty surprising for most people. All right, so some training details, and that's what we're going to get into now. They trained the network on 8 Tesla V100 GPUs for 4 days, and then they didn't observe any sort of improvements. And then also their implementation used an adaptive mini-batch size, depending on the output resolution, so that the available memory budget was optimally utilized. So I guess they just decreased the batch size when they couldn't hold that many into memory. So yeah, let's move down to the appendix where they actually go through the details of this. So here is sort of what the generator and discriminator looks like. So in the beginning, we have this, for the generator, we have this latent vector, right? This noise vector. In this case, they specify that the SED dimension should be 512. And then, so I guess that's this, and then they map it to 512 also. But this is, you know, so the in channels is 512. In this case, they are similar, but you can imagine that you would change the set dimension and then have another in channel. But so they follow this pretty nice trend where they use this, in the beginning at least, they use a transposed convolution. So that is a transposed convolution, a 4x4 that maps this 1x1 to 4x4, and then they use a same convolution with a 3x3 filter right there, which you know, just works on this 4x4 image. And then they upsample, right? So they upsample right here to 8x8. They do 2 3x3 same pattern conv layers, and then again upsample, and then the similar pattern. And then we can see that they used Leaker-ReLU right here. And so, you know, it's this pretty simple trend. And in the end, eventually we'll also add this in the end. So we'll add this 1x1 convolution that maps this in channels right here to this RGB. And I guess, you know, one thing here is that when we're doing this progressive growing, right, this is just for 1024. It's going to look a little bit differently when we do it for a specific input, for a specific image size. So, you know, let's say we're just doing it for 4x4, then you would remove all of this stuff, right? And suddenly the RGB layer is in between here. So the RGB layer is right here because the output will be 4x4. So when you're done with that, what you cancel out will differ. So you will remove, I guess, now all of these stuff. And then there will be another RGB layer that's in between here. And then you sort of do that over and over until you eventually reach the end. So I guess, you know, to be, what would perhaps be a little bit clearer is that they also use, you know, RGB in between all of these ones when they're actually training the network. But this that they show right here is what it will look like when it's done. And so for the discriminator, you know, they sort of do this opposite approach where they, in the beginning, take this RGB and converts it to 16 feature channels, which is what they had, you know, before they. So you can sort of see that it's the opposite, right? Sort of a mirror image. And then they follow this similar approach using 3x3 conv layers, same padding, but instead of upsampling, they downsample with an average pooling. And yeah, pretty much the same thing as we saw before. I guess what is important to note is this MiniBatch standard deviation that we talked about. which they do in the end because they noticed that it had better results if they did it there. So you can see that we have 512 channels here, and then we have 513, and that is because they sort of concatenate the MiniBatch standard deviation so that we get 512 plus 1, and then we run it through this last 3x3 and 4x4, and in the end they also have this fully connected layer right there to map I guess 512 channels to one channel. And all right, so that's the network, sort of the exact architecture. Then they mention here that the last 1x1 of the generator is 2 RGB, which we saw previously, and then the first in the discriminator is from RGB. They mention here that they start with a 4x4 resolution and train until the networks have until we've shown the discriminator 800,000 real images in total. And then they alternate between two phases, fade in the first 3-layer block during the next 800K images, and then they stabilize the network for 800K, and then they fade in the next, etc. So, one thing that is kind of sneaked in there when I looked at their implementation is that they also use this batch repeats. So for one batch, they actually do 4 update steps until they show a new batch. But I didn't see that they mentioned this anywhere in the paper, but it was in the official code, at least from my sort of what I was understanding from the code. But I didn't use this just because it wasn't mentioned explicitly in the paper, so I didn't do this. But that's just one thing to keep in mind, is that perhaps you would need to do this, for a little bit more images to get same quality. All right, so they mention also that their latent vectors correspond to a 500-dimensional hyperspace, just set dimension 512, and the generated images should be in the range -1 to 1, leaky ReLU with slope 0.2, except for the last that uses linear activation. And as they mentioned previously, there's no batch norm, layer norm, or weight normalization in either network, but they use this pixel normalization of the feature vectors after each COM 3x3. And also notice that this is only in the generator, and I'm not exactly sure why you don't do it in the discriminator. I guess the generator is more sensitive to sort of normalization and sort of things like that. But yeah, I'm not really sure why they don't do that why you don't normalize in the discriminator. And yeah, they also mentioned that they inject the across MiniBatch standard deviation as an additional feature map at 4x4 resolution towards the end of the discriminator, and then the upsampling and downsample corresponds to 2x2 element replication, and so nearest neighbor interpolation and average pooling. They train the networks with Atom, and then they use alpha 1e-3 and beta 1, so the momentum term of Atom they set to 0, and then beta 2 they set to 0.99, and that is exactly similar to what they did in the vegan GP paper. So they just kind of copy that. I guess the learning rate is perhaps different, but those two are the same as vegan GP that we've taken a look at previously. So let's see, what did they mention also? Well, I didn't do this, but for visualizing the generator output, they use an exponential running average of the weights for the generator with decay 0.999. I guess that's sort of just for stability, so that the images don't vary too much during training. So I didn't do that, and it still gets pretty good results. So I think that's sort of a detail that's not too important. And they use a mini batch size of 16 for those images, and then they gradually decrease the batch size because I guess they couldn't use that large, right? Because of the memory budget. And yeah, so one thing that's different from vegan GP is that they used nCritic to 1. So nCritic in the vegan GP was 4, which basically meant that we updated the discriminator 4 times, and then we updated the the generator once. So they just updated discriminator once, generator once, more sort of a standard setup. And also one thing they also introduced is this fourth term into the discriminator loss, where they sort of the reason was to keep the discriminator output from drifting too far away from 0, right? Because the critic doesn't have this to be between 0 and 1 for its output. It can generate any output value as long as it's trying to separate the generator and the real images. So what they do is that they just add this term right here, where they take the original loss and then they multiply some small constant times the sort of the mean of the discriminator on the real images squared. So yeah, that's just to make the critic, I guess, output values that aren't too far away from 0. And yeah, that is it. That is it for the sort of the details of this paper and the most important parts, in my opinion. In the next video, we are going to implement this. And I'm pretty excited because I think I got pretty good results. I did not train it to 1024 images though. I trained it to 256. But I think, you know, if we would just train for longer, we would get pretty good results. So I'm pretty excited for that video, and hopefully now you also have a good understanding of this paper and are ready to tackle the implementation. All right, thank you so much for watching, and I hope to see you in the next video.